Hi, Astronomy. Mr. Janowski here. This is part 9 of the chapter 13 slides. In the last part, we learned about this very useful kind of graph that astronomers use to compare different things about stars. I'm not going to tell you the name of the graph or what things they're comparing because it would ruin my do now questions. So without further ado, let's do the do now questions. So, what is the name of this type of graph? This is an HR diagram, a Hertzsprung-Russell diagram. So what does it compare? Well, if you look at the axes, you have your answer. It compares luminosity on the y-axis and temperature on the x-axis. And remember, there are weird things about this. Both of these scales are logarithmic, and the temperature scale, for historical reasons, the convention is to kind of do this one backwards, meaning you start with your big numbers on the left, and the numbers get smaller as you go to the right. We could totally do it the other way, but we do it this way because this keeps with the "oh, be a fine girl, kiss me" thing. So that's why they do it. So on this diagram, this is an HR diagram, but I've added, the authors of the textbook added these green lines here. So these lines show stellar radii calculated by taking the Stefan-Boltzmann law and finding a relationship between R and L and T. So yeah, if you plot this, even though this is to T to the fourth, this is R squared. Yeah, it looks weird. But if you plot this kind of thing on a log graph, you end up getting straight lines, even though it's an exponential. Don't worry about it. It's a math class thing. But anyhow, one useful thing we notice about this. So here's the sun right here. So let's think of this line here. And notice that most of the main sequence, not quite all of it, but most of the main sequence is within one green line going up or down of this. So yeah, there's a little bit beneath that there. There's a little bit above it here. But most of your main sequence is within one of these lines. So each of these lines represents a factor of 10. So what this is telling us is that most main sequence stars are within a factor of 10 in terms of their radius compared to the sun. So what does that mean? It means the biggest main sequence stars have a radius maybe 10 times that of the sun, but not much bigger than that. And the smallest main sequence stars have a radius maybe 1/10 the size of the sun, but not 1/10 the radius of the sun, but not a whole lot smaller than that. Most of the main sequence stars fall within that area there. So that is just main sequence stars. Like it says here, your red giants can have radii that are 10,000 times greater than that of the sun. So yeah, if you're going from this line, if you go up, we're now 10 times bigger. Now we're 100 times bigger. Now we're 1,000 times bigger. And according to the textbook, there are still stars that are even bigger than that. So way up there. So yeah, Betelgeuse is about 1,000 times bigger in radius than the sun. And you can have a white dwarf that's only about 1/100th the radius of the sun. So 2 orders of magnitude smaller. So 1/10 of a tenth is what 2 orders of magnitude smaller means. But those are white dwarfs down here, and these are red giants up here. Again, the key idea is that most main sequence stars, most stars that are in the regular part of their life doing their regular thing, are going to be about the size of the sun, maybe a little bit bigger, but not much more than 10 times bigger, and maybe a little bit smaller, but not much smaller than 1/10 the size of the sun. That's the whole point of this. So there turns out there's also a relationship between the mass and the luminosity of these main sequence stars. So 1924, this guy Eddington, who also has an aside, he got some of the early evidence for Albert Einstein's general theory of relativity by taking photographs during an eclipse in 1919, but that's a different story. So anyhow, Eddington also discovered this relationship between mass and luminosity for main sequence stars. And the relationship is this. Your luminosity, so these are going to be in solar units. So 1L would be 1 times the luminosity of the sun. 1M would be 1 times the mass of the sun. And it turns out that your luminosity is very strongly dependent on the mass. So luminosity goes has mass cubed. So again, this is true only of your main sequence stars, not of your white dwarfs, not of your red giants, things like that. Just your main sequence stars. So how do you apply this? So if we're comparing a main sequence star that has twice the mass of the sun. So maybe this is a star that's in a binary system, and we took measurements, and now we know, the mass of that star. If it's got twice the mass of the sun, how is its luminosity going to compare to the sun's? Well, L is equal to m cubed. So in this case, m is 2 times the mass of the sun. If you cube 2 times 2 times 2, you get 8. So this is telling us that this star would have 8 times the luminosity of the sun. So even though it's only twice as big, it's putting out 8 times as much light. So, that's shown on this graph here. And this graph here is showing a plot of, this is not an HR diagram because this is not temperature. You've got luminosity on the y-axis again, but you have mass on the x-axis. And if you plot all these things, you get kind of this relationship. So this, yellowish gold line here, this would be exactly the luminosity is proportional to mass cubed. So it's not exactly that line, but it's fairly close to that line. So that's your mass luminosity relationship. So since most main sequence stars have a mass that are within about a factor of 10 of the sun, that means most main sequence stars are going to have a luminosity between, if they have 1/10 the mass, 1/10 cubed would give you 1/1000th of the sun. And if they have 10 times the mass, that means they would have 10 cubed, or 1,000 times the luminosity of the sun. I swear what I just said is true. I don't know if it made sense the way I said it, but it is true. So since most of your main sequence stars are within, again, there are exceptions. So here's the sun here. Your more massive ones going this way, there are a few that are more than 10 times. So this guy up here is about 20 times the mass of the sun. But if it's only, 10 times, it'll have about 1,000 times the luminosity of the sun. And your least massive stars down here, with a mass of 1/10 out of the sun, it would be about 1,000th the luminosity of the sun. So not exactly true, this relationship, but a pretty good indicator. It gives you something to go by. So spectral types continued. So spectral types again, this is the OB a fine girl kiss me thing. So OB, A, F, G, K, M are your most important spectral types, which we credit Annie Jump Cannon with coming up with this system. She took the old system, simplified it, reorganized it in a more sensible way. So Annie Jump Cannon came up with OB, A, F, G, K, M. And then a colleague, they're academics, they're not coworkers, they're colleagues. Her colleague, Cecilia Payne-Gaposchkin, she figured out why the system worked. So good on Cecilia Payne-Gaposchkin. So it goes a little beyond this. So you don't just have your spectral types. You actually, if you want to be really specific, you can assign this other number to them. So the numbers go from 0 to 9. We don't start with 1. We start with 0 and go to 9. So 0 is the hottest one in that class, and 9 would be the coolest. So again, that seems a little backwards. The bigger number is the cooler one, but that's how it goes. So the way this works, you go by the letters first. So all B's are hotter than all of the A's. So don't worry that, the 9 should be cooler than the 0. No, that doesn't matter, because a B9 is still going to be hotter than an A0. But within one particular letter of spectral types, so now we're talking just the A's, an A0 is hotter than an A1, and an A1 is hotter than an A2, and so forth, all the way down the line. So, it's not just these 7 different letter categories. Each letter category is divided up into 10 subcategories if you're getting really particular about the temperature of these stars. So beyond that, we also have this thing called luminosity classes. So these are based on the widths of the spectral lines. So what spectral lines are there, those tell you the spectral types. The widths of the actual lines themselves tell you the luminosity class. So the width of the spectral line depends on the star's luminosity. Now follow the asterisks. It actually depends on the star's density, but that's very closely related to the luminosity. So we're just going to say that the width of the spectral line has the star's luminosity. And Yeah, the width of those lines determines the star's luminosity class. So once again, we have a system that evolved over history kind of organically and ended up not being as nice as one would hope. So it goes 0, 1A, 1B, 2, 3, 4, 5, 6, 7. So yeah, this is why you have, is that 9 total? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, you have 9 luminosity classes in a system that goes 0 through 7. Not my fault. That's how history worked out. So if we're looking at the luminosity classes, there are stars. Again, we're just going to divide stars into dwarfs and giants for the most part. But there are extremely huge hypergiants. So these guys would have a luminosity class of 0, but there aren't very many of those. So next you get to the ones. So in your ones, you have 1As and 1Bs. So these are bright supergiants and supergiants. So these guys are way up here on the HR diagram. The most important one for us are the main sequence ones, of course. These are the stars doing their regular old thing. And all main sequence stars are luminosity class of 5. So if you're looking at this graph, I know it gets kind of complicated, but here's your main sequence going down through here, and here is the Roman numeral 5, indicating, that these are the main sequence. So our sun, yeah, it's a G star. Well, technically it's a G2 because it's a little bit cooler than a G1. But yeah, it's a G2, or you might call it a G2-5. I think you would actually say 5, not G2V. So the sun is a G2V. It's on the main sequence. V tells you that. It's a G. So here are our spectral types. The sun would be here in the Gs. And it's a G2 because, again, it's not the hottest of the Gs, but it's fairly close to being the hottest of the Gs. And you have other stars. 4D Eridani is a low luminosity main sequence K1V. So find the Ks, would be up in here, and it's a K1, so it would be one of the hotter ones, so probably close to about here is where 4D Eridani would be. Also main sequence. Arcturus is a high luminosity giant, so that's a K13. So Arcturus and 4D Eridani are about the same temperature because they're both K1s, but they're different luminosity classes. So you would find 4D Eridani over here, and Arcturus, being a giant and a luminosity class 3, would be up here. And your least luminous stars, these are class 7. So these are going to be the white dwarfs down here. So they can be very hot, but they're not going to be very luminous. They're low on this graph. So here are just some other examples. Betelgeuse and Rigel are both 1As. Antares, a supergiant, is 1B. Polaris, a star we like a lot. That's a luminosity class 2. A regular giant, Aldebaran, is a 3. Subgiants, Procyon. So that's the brightest star in Canis Minor, the little dog, Canis Minor. Procyon is a luminosity class 4. And main sequence stars, like the Sun and Sirius, all of those stars are class 5s. So, one more useful thing. So back to this picture of, I think the Arc de Triomphe on the Rue de whatever. I forget what it's called. Champs-Élysées? Not the Rue. Champs-Élysées. I don't know. I've never been to France. So anyhow, back to these streetlights. So imagine you were standing here by this streetlight, and you're close enough to this streetlight that maybe you could get out a tape measure and measure the distance to that streetlight. So now you know your distance. And you have a light meter, a photometer, so you can measure the brightness of the streetlight. So you can take all that information, plug it into this formula here, and figure out the luminosity. So now that you know this, how can you figure out the distance to this star? So your tape measure is not long enough. You can't, take it and measure the distance just the old-fashioned way to this, I think I called it a star, this streetlight here. Well, you already know the luminosity of this one, and you know all of these bulbs are identical, so you know all the luminosities of all these guys are the same. So what you can do is take this formula, solve it around differently. You do some algebra, you solve this expression for D, and now you have D is equal to this, root of luminosity over 4 pi times the brightness. And because you know the luminosity of this one, by figuring out the luminosity of this one and being clever and realizing they're all the same bulbs, so they're all equally luminous, and you can measure the brightness of this bulb just using your light meter. So point your light meter at this thing, measure its brightness, plug it into here, and now you can figure out the distance. So this is a clever way of figuring out the distance to things that are too far to directly measure the distance to. So when this kind of situation comes up in astronomy, we call stars like this standard candles. So yeah, cute picture. I like this picture. So the way standard candles work, very similar to what we just did with the streetlights. So maybe there's a star that's close enough that you can measure its distance fairly directly using parallax. So now you've measured D. So you can measure the brightness of that star just using a photometer, a light meter. Just point it at the thing, take a measurement, and figure out how bright the star appears to you. So now that you know D and B, you can plug it into this formula down here, and you can figure out the luminosity L. So if you have some reason, and we'll get into this mostly in the next chapter, I'll talk about it a little bit here in an upcoming slide, but if you have some reason for believing that a very distant star, so it's too far away to measure using parallax, but if you have some reason to believe that this star's luminosity is the same as this star, you can figure out its distance by doing all of this. So now you're going to assume L is the same for this star and this star. You again just measure the brightness of this star using your photometer, throw it into this formula, and you get the distance. So how can you figure out the star's luminosity? How can you, assume that this star that's so far away you can't measure its distance, how can you figure out, well, it's actually putting out as much light as this one is? Sometimes you can do it by its spectrum. Sometimes you can do it by where it is on the HR diagram and get a rough idea of how luminous it actually is. Maybe you saw it in a binary and you can figure out its mass that way. And now that you know its mass, you plug it into the luminosity-mass relationship. So now you know its luminosity. And maybe you can figure it out because it's a pulsating star, which is something we'll do in the next chapter. So you can measure how long it takes for this star to pulsate, go bright and dim and bright and dim. That's what Henrietta Swan-Leavitt, that was another one of Cecilia Panga-Pashkin and Annie Jump Cannon's colleagues. She worked with pulsating stars and figured out important things on those. You could figure out its luminosity that way. And then sometimes we have a particular type of binary star where one star will go supernova with an extremely high luminosity. And the important thing, not only is it very bright, but it's also a known luminosity. We know how luminous it was. And when this happens, you can use those things to measure the distance to a very distant galaxy. So useful things for figuring out, the big scale of all the stars and galaxies out there. So this is a graph. This is a slide just showing you a lot of the different ideas we've done in this chapter. So yeah, HR diagram, main sequence. Here we have these guys here. We've got binary stars going around. This is how you can figure out the total mass of binary stars. Here we've got parallax and the distance parallax relationship. Different spectrum here. The Stefan-Boltzmann law right here that relates luminosity, radius, and temperature. So this slide doesn't apply to us, but this is where we would be. Ideally, we'd be finishing this up at the end of quarter 3. But as you're aware, this year has ended up being very weird. So what is the mass-luminosity relationship for main sequence stars? How does L relate to M? L is equal to M cubed. So luminosity is very strongly dependent on the mass of the star. So what would be the luminosity of a star with 2 times the sun's mass? Well, it would be 2 cubed, 8. So if a star is twice as massive as the sun, it will be 8 times as luminous as the sun. So it'll put out a lot of light. We'll get into this idea more in the next chapter and what effect this is going to have on the lives of the stars. So what is the luminosity class of a main sequence star? Well, here's your main sequence, and these guys are V, or 5. Main sequence stars always have a luminosity class of 5. So what do we call those stars that are useful for determining distances because we can just measure their brightness and we have some reason of knowing their luminosity? We call these stars standard candles. So these are very important for figuring out the large scale structure of the universe in terms of how far away galaxies and stars are. And back to Henrietta Swan Leavitt, real quick. I know this part of the slide is getting long, but Henrietta Swan Leavitt, she's the one who measured variable stars, and she measured them in these distant. We didn't. This is the whole point of the story. We didn't know they were separate galaxies at the time. We saw different shapes, these nebulous clouds of things, and there was a big argument: are those separate galaxies like our own that are very far away, or are those just features of our own galaxy? And we didn't know the distances to them until Henrietta Swan Leavitt came along, did all these measurements of these variable stars, figured out a very clever way of determining the luminosity of a variable star. And then when we saw these stars in these clouds, these nebulous things, these cloudy looking things, and because they were variable stars, we could figure out their distances. Because they were variable stars, we could figure out their luminosities and then throw that into this. So Henrietta Swan Leavitt gave us a way of knowing L. You can measure B with a light meter. And it turns out that these stars were incredibly far away, more than hundreds of thousands of light years away. So her contribution kind of settled the whole argument, which has only been known for about 100 years, that we're not the only galaxy. We had seen other galaxies, but people were arguing, are those actually separate galaxies or are those just clumps of stars in our own galaxy? So she figured it out. But I'm rambling. This part has gotten too long. But on the other hand, this is the last part of the slides for chapter 13. So hopefully you found that helpful.